Let's talk about polynomial functions and their graphs. Okay. So in our first example, we are given a graph of a polynomial, and we're asked to determine all kinds of information based on this graph. Okay. If you notice that this graph is disjoint, it has breaks in it, and that's not okay because our polynomials are continuous. They can be drawn without lifting your pencil, and there are no sharp turns. So what we're first going to do is work our way from left to right and connect our graph. Now, if we're looking at the left-hand side, you may not know if we need to connect upwards or connect downwards. So you may need to work backwards a little bit. But if we're looking at this middle part, if they have to connect, that means that the only way to connect the left side is up top. And then I'm going to draw little arrows to let myself know that my graph is continuing, and it also lets me know the end behavior. Now that we have our graph complete, at least a guesstimate, we can start answering the questions. Is the function even or odd? If you notice, the arms go the same way. To the left, we go down. To the right, we go down, which means that our function is even. Remember, if they're odd, your end behavior goes in opposite ways. Part B, is the leading coefficient positive or negative? Remember, look at the right side. Since our right side of the graph falls, we're going down for our end behavior. If we're going down like a frown, that means that our leading coefficient needs to be negative. Finding all zeros of the function, that's where you need to go along the x-axis, because remember, zeros are roots, are solutions, are x-intercepts, and we need to find where we cross or touch the x-axis. So we have one right here at -2, another one here at 0, and then we touch and turn here at 4. So our zeros of the function are x equal to -2, x equal to 0, and x equal to 4. Part D asks where the function crosses the x-axis. Remember, crossing means that you go from above the x-axis to below or below to above. So for instance, working from left to right, at -2, our function goes all the way across. So at x equal to -2, the function does cross. At x equal to 0, working from left to right, our function comes in, kind of flattens out a little bit, but then it does cross, which means that x equals 0 is a 0 where the function crosses. And we know it crosses because it goes from above the x-axis to below. And at x equal to 4, our graph comes up, touches, and comes back down, which means that it touches and turns at x equal to 4. This is taking all the things that we learned about polynomial functions and then giving us visuals on them. So part F, which x-intercepts have even multiplicity? Remember, the behavior of the zeros was determined by the multiplicity. If you have even multiplicity, that means that you touch and turn at the 0 or x-intercept or solution or root, all the same thing. And then our graph only touched and turned at x equal to 4. So that is our only x-intercept with even multiplicity. Remember that odd multiplicity occurred whenever you crossed the x-axis. So if we go back up, we crossed at x equal to -2 and x equal to 0. Part H asks, based on the turning points, what is the minimum degree that this function could have? Remember that the max number of turning points was equal to our degree minus 1. If we solve this equation for n becomes our turning points plus 1. So if we want to get from our degree to max number of turning points, we subtract. But if we want to go from number of turning points back to the minimum degree, we add. So let's go and look for our turning points. We're going to start from left to right, and I want you to pretend you're driving a car. I know that sounds ridiculous, but this polynomial graph is the road that you are driving on. So starting from left to right, we would be driving. We have to turn the wheel. Whenever you have to turn the wheel to stay on the road, that becomes our turning point. So we have our first turning point. Then, all right, we made it around the curve coming down. Here's another turning point because we're having to turn the wheel to stay on the road. But notice how it flattens out a little bit here. It's like a little S curve, which means that we have to turn the wheel back to stay on the road. So that's our third turn. Coming along. Another turn. We're turning the wheel one way to remain on the road. So turning it to the left, stay on the road, which means that we're only counting it as once. But then we hit x equal to 4. That is another turning point because we have to hit the wheel really hard to the roadside and come around the turn. And then we go off into the infinite, which means that we have 5 turning points. And if we have 5 turning points, n is going to be 5 plus 1, which means our minimum degree is 6. Which does make sense because we said that our degree was going to be even because the arms are the same. If we would have gotten an odd minimum degree, that would have been really off because we said we were going to have an even function. All right, the last part, and this is where it gets a little confusing for students sometimes, so make sure you're paying attention. We need to find the least possible degree, which means that least possible degree better be n equal to 6, function in factored form that could represent this graph. Okay, so we have a lot of things going on. Let's start with our zeros. We have x equal to 4, x equal to -2, and x equal to 0. Much like when we wrote the quadratic function from the x-intercepts, we're going to work our way backwards. It's the same type of initial process. The x equal to 4 came from x minus 4. The x equal to -2 came from x plus 2. And then x equal to 0, you could write x minus 0, but you know that mathematicians are lazy and we will just write x. Okay, so here are our factors. Let's put them all together. I'm going to name my function p of x since he's a polynomial. We have x minus 4, x plus 2, and then x minus 0, or x. Couple of things. We said way back in part B, scrolling up a little bit, that our leading coefficient was negative. Since we're going for the minimum, we are going to do -1 out front. Again, that is because of our negative leading coefficient. Okay. We also have to take care of our multiplicities, which were our exponents, because right now we don't have anybody touching and turning, and we don't have the extra turning points that we would need to make a degree of 6. Right now, all we have is a degree of 3. We said x equal to 4 had an even multiplicity, which means that first even number we know is 2. So his multiplicity is going to be 2. The x plus 2 and the x are both odd multiplicities. We have to figure out whether it's going to be a 1 or a 3. And for that, we look back at the graph. If you go straight across, you don't take your time, it's just literally from below to above or above to below, no turning points, that's going to have degree 1, which means our x plus 2 factor has an exponent of 1. However, at our x equal to 0, notice that we had turning points 2 and 3. It flattened out a little bit and made us do some turning. Whenever you have a turning point happening at your 0 and you're still crossing, we're going to have a minimum multiplicity of 3 because it doesn't go straight across. Remember, one of the multiplicity characteristics was if k is greater than 1. So if your multiplicity is greater than 1, you tend to flatten out as you get close to the 0. Now, if we look at the degree, we have 2 plus 1 plus 3 gets us 6, which is our minimum degree. And our very last step, I'm just going to make this look a little bit nicer because I hate that x cubed hanging out at the back end. So I'm going to say p of x is equal to my negative x cubed times x minus 4 squared times x plus 2. And if you want to include the 1, you can. I have no problems with that. But remember, it's the same thing as x plus 2 without any exponents written.